be looking at the prediction of the physical sciences paper 1 for the forthcoming examination. Okay, so in normal cases, the paper is out of 150 and it's a 3-hour paper. Okay, so in that we expect 10 multiple choice questions, and then we also have some structured questions that will account for 30 marks. So for these 10, each question will be 2 marks. Okay, and as much as it's a multiple choice, but there is some bit of reasoning, some bit of calculations that might be involved. And it's usually a combination of all topics, so it cuts across. Okay. And then from that, we shall break down some topics and also look at some sample questions that we can work with as we enforce, or we go into detail of what is really expected. Okay, so as per the weighting of the paper, we shall have mechanics. Mechanics is going to carry most of the marks, which is like maybe 65 plus minus, okay? And then the waves, sound, and light shall have 15 marks plus minus. Then electricity and magnetism will account for plus minus 55, and then matter and materials will go for 15 marks, okay? So those marks will be cutting across all the levels, as we can see here. At least for level 1, level 2, 3, and 4. So the most complex is going to carry more or less the least amount of marks. Okay, so skills in physical sciences: identify the question phenomena, formulate an investigative question, and all of this. This is basically things that we always cover in classes, okay? Listing all the possible variables, a testable hypothesis, and so on and so forth. How do we identify the variables, the dependent, the independent, and the control? At least we need to know and remember all of this. List of appropriate apparatus. This is mostly vital when you're doing your practicals. Okay, so under graphs, what we need to know, how to draw at least some graphs if you're given information. Okay, this normally comes under mechanics, where they ask for velocity time graph or position time, and even under electricity. Let's say that they've given you the relationship between current and then the voltage or the potential difference. And then how do you interpret them? That's also vital. And then how do you draw conclusions from those graphs? Then calculations using 2 or more steps, and so on and so forth. And then the knowledge of grade 10 and 11 will be vital also, because we need to know some of those aspects, because when you look at some topics, most of the work that is usually tested is probably from grade 10 and okay, so I'll skip this part of the guideline, and then we look at how we elaborate the content. Okay, so these are the topics that will be covered. Number 1, you look at Newton's laws and their application. Remember, we have quite a number of laws of Newton. Okay, so we have the laws of motion, and we know that these are law 1, law 2, and law 3. At least we should be in position to state them and even work around them, okay, especially with the formulas and stuff. Then we also have the universal law of gravitation. So those are the 4 laws that we mainly need to put our emphasis on. Okay, so below this, we have different types of forces. An example, we have weight, we have normal force, frictional force, applied force, tension, and so on and so forth. So we need to know how to at least define a normal force, okay? How do we define frictional force, and then static frictional force, and the formulas and so on, okay? Then solving problems that deal with friction. So for as long as we know that our frictional force, whether kinetic or static, is the mu s and then the normal force. So this mu is basically the coefficient of the friction, static or kinetic. And then there's a note where they are telling us that if a force F applied to a body parallel to the surface does not cause the object to move, F is equal in magnitude to the static frictional force. And then the static frictional force is maximum just before the object, starts to move. So static friction is basically that force that keeps the object in one place without any motion. So this formula is quite important as we shall move on. Then two, we also need to know how to draw our force diagrams or the free body diagrams, okay? Because in almost all papers, there's always an element of draw a free body diagram, and those are marks that we should not leave out, okay? Just get all those marks. So draw the force diagram, draw the free body diagrams, and indicate the forces and so on and so forth. So this, even the mark allocation should guide you. If they're giving you like 3 marks, we expect at least maybe 3 forces around, at least, which means the minimum should be 3 forces acting on that body. And then we need to remember how to resolve forces, okay, into the horizontal and then the vertical components. And then how do we determine the net force as well as the direction? Okay. Then under Newton's first, second, and third laws, you need to know how to state the first law, which will be a body will continue in its state of rest or uniform motion unless a non-zero resultant net force acts on it. That's the way it is. Now, in most cases, there are certain keywords that are important, like 1, remain in a state of rest or motion. And then we also have constant velocity and then the non-resultant. So this key statement, if some is shorting, then you'll probably be penalized. And then we also need to discuss why it's important to wear seat belts using Newton's first law. So this is more like the application. Okay, why is it relevant to wear seat belts? Okay, and then also when it comes to the airbags and so on and so forth, then we need to know how to draw force diagrams, free body diagrams of that are in equilibrium or accelerating. Okay, apply the laws, moving on a horizontal plane without friction, with or without friction, and so on and so forth. Okay, and then we also look at the two body systems. This is usually something that they like, okay, as examiners. Then state Newton's third law that when an object A exerts a force on object B simultaneously also exerts opposite one, and so on and so forth. Then be able to identify the action-reaction pairs and then list the properties of those pairs. And then there was Newton's second law, I haven't said, but we also need to remember it, okay, because that is the F net one. Okay. Then we also need to know Newton's law of universal gravitation. They hardly ask this under structured, but under multiple choice, it's usually an issue. Okay. Know how to state the law itself and then the formula itself. Okay. Then describe weight as a gravitational force the Earth exerts on any other object. How do we calculate weight? Is the product of mass and the gravitational force. Calculate the weight of an object on other planets and all of that. Distinguish between weight and mass. This is also something that is always an issue with people. So remember, mass is basically the measure of content within an object, and then weight is just the product of mass and then the gravitational force. So explain weightlessness. So that is more like a feeling, weightlessness. Like an object does not have a normal force. Okay. Shall go into detail if we come across a question of that sort. The next, still under mechanics, we need to look at momentum and impulse. How do we define momentum? Okay. How do we describe linear momentum as a vector quantity with the same direction? How do we calculate momentum of a moving object? There is the formula, and we also have such formulas on the formula page at the back, okay? How do you describe the vector nature of momentum and then illustrate this with examples, draw the vector diagrams, and so on and so forth, okay? There we are, Newton's second law. So this and momentum usually go hand in hand. Okay, so how do you state Newton's second law? There are still keywords, okay? The net force acting on an object is equal to the rate of change in momentum and so on and so on. Okay, so this is just a simplified version of the momentum. And then there's that other one that talks about proportionality and so on and so forth. So F net from Newton's second law will be given as this. the rate in change in momentum over the change in time. Then we need to explain how does the net force and change in momentum of various motions occur. And then how do we calculate the change in momentum? That is P final minus P initial. So momentum final minus momentum initial will give us our change in momentum. Okay. Then we also need to at least understand the effect that will be caused as we increase in the direction of motion, especially with the rocket engine fires. What happens with the decrease if brakes are applied, if we have some sort of reverse direction or reverse motion, what goes on, okay? Then next we have impulse, and we know that impulse is the product of the resultant net force acting on an object as well as the time. So force times time can be F net. Then we have this formula. We just need to remember how it works, how it goes. Then explain the concept of impulse as it applies to safety consideration in everyday lives like airbags, seat belts, and then arrestor beds, okay? Then we have conservation of momentum. So in this, you just need to explain or state the law of conservation of momentum, okay? Then an isolated system, you just need to know it, okay? You need to know what a system is, and then internal and external forces. That is basic that we need to know. So this we need to know, okay? Know how to state this, that the total linear momentum of an isolated system remains constant. Then we need to know how to apply this and then distinguish between elastic and then inelastic. So the confusion usually comes when they say, I've seen learners giving reasons like inelastic is when objects collide and then they separate and move separately after the collision. That is wrong. Okay, it's not more like elastics in clothes and rubber bands as no, it's completely different. In this case, remember momentum from the law of conservation. Momentum is always conserved for both elastic and inelastic. The only difference lies within the kinetic energy. Okay, so kinetic energy within the elastic is conserved. Okay, within the inelastic, it's not conserved. So what we mean by this is that the EK initial is equal to the EK final when we're talking about the elastic collisions. If it is inelastic, okay, the EK initial is not the same as the EK final. Reason for that, there is probably loss of energy through sound, through heat, or even light. That's why the energy will not be conserved and bodies will be considered inelastic if this condition is met. Okay. Then still under mechanics, we have the vertical projectile of the VP, and in grade 12, we only focus on the 1D, okay, one dimension. So explain what a projectile is: an object with an initial velocity and then moves under just the influence of gravitational force. Define free fall, okay, just know the difference between a projectile and then free fall. Then use the equations of motion and know which one exactly to use, okay, based on the given information of variables. We need to know how to sketch the position time graph, velocity time graph, and then the acceleration time graph, okay? So you can always revisit some of the videos that we've done before when we're explaining some of this content in detail, okay? So we need graphs for a free-falling object, one object that is thrown upwards, object that's thrown downwards, and then an object that is bouncing, okay? So from the graphs, we also need to know how to determine the position, the displacement, the velocity or acceleration at any time, okay? Then still from the graphs, we need to look at the motion of bouncing, thrown vertically upwards, and then basic, okay? Then we have the work, energy, and power. Define what work done is. and then the constant force and how it works. Then we need to be able to draw force diagram and free body diagrams, usually on the incline. Calculate the net work done on the object, distinguish between positive net work and then the negative, okay? Work done on the system and then the work done by the system. Then we love this, the work energy theorem. You need to know at least how to state it in words and then how to apply it under the calculations, okay? So you need to apply it to horizontal, vertical, and then inclined planes. And then the conservation of energy. So it's a two-way. Number one, you need to define what conservative force is. The force for which work done in moving an object between the 2 points is independent of the path. An example, you look at the gravitational force, the elastic force in a spring, and then the electrostatic force. So these are automatic. Directions are just having not, let's say, the directions are already determined in which the work is going to be done. Okay, that's why we say that the direction is independent. In other words, the work does not depend on the direction because we already know what's going to happen with the directions. Then the non-conservative, saying which work done in moving an object between will also depend on the path. An example, frictional force. We know that the direction of friction will always depend on the motion. Okay, so if the motion is moving east, friction must move west. Okay, and so on and so forth. And then we should be able to state the principle of conservation of mechanical energy. So mechanical energy is just a combination of the EK and then the EP. Okay, the gravitational and then the kinetic. So this usually applies to an object that is midway, okay, from the point of projection towards the end point. So in between, that's when it has both the EK and the EP. So they're telling us to solve conservation of energy problems. We can use this. The change in EK plus the change in EP, we get our that. And then I use the relationship above to show that absence of non-conservative forces, mechanical energy will always be conserved. And then power, like we define power as the rate at which work is done, expanded, and then we use this formula, calculate the power involved, perform calculations, and so on and so forth. So I'm going to stop here with just this guideline for now. Let me just look at the sample questions, and then we shall come back and carry on with our expectations. Okay. Now I'll start with the multiple choice, in as much as most people, I don't know, feel it's kind of obvious with the multiple choice. Let me choose this. Okay. So in this case, options are always given. Okay, you just have to choose what is correct. Now, you can use different options to answer these multiple choice questions. So you can, there's an option of elimination. Eliminate what you feel is wrong, and then you'll be left with the correct answer. Or if you know what is going on, just go straight to the correct answer and then circle what is left. Okay. So the question tells us that a car is moving at a constant velocity. It's even in bold. Which of the following statements about the forces acting on the car is correct? 1, the net force acting on the car is 0. 2, there are no forces acting on the car. The weight of the car is equal to the normal force acting on the car. And then there is a non-zero net force acting on the car. Wow. So one thing we know is that for as long as a car is moving at a constant velocity, which means the V final is the same as the V initial. Let's start with option number 1. They're telling us that the net force, how do we calculate net force? F net is equal to MA. Okay, and we know that M is the mass, this is the acceleration. So literally, for as long as the velocity is constant, there is no change that is happening within the velocity. So which means our acceleration is going to be 0. We know that acceleration is given as the change in velocity over the change in time. Yes, time will be there, but then the change in velocity is going to give us a 0. So for as long as the acceleration is 0, which means the net force is also 0. So I feel like this option is the correct option. Okay, so I already have a correct option. So these ones, there are no forces, that's wrong. I mean, there's always a force that must push the car forward. Okay, and then there's always friction that must try to bring the car down. And then the weight of the car is equal to the normal force that is acting on the car. I mean, this is okay, this is true. But then we're talking on a car we're talking about a car that is moving. This is possible if the car is stationary and there's nothing else. And then there is a non-zero net force. No, this is wrong because we said the net force is 0. So option A would be the best suited for that. And then 1.2, a ball is projected vertically upwards. We ignore resistance. Which of the following statements about acceleration of the ball at its maximum is correct? Statements about acceleration is correct. So we know that for as long as the ball is projected back upwards, there is just one acceleration, which is g. It's more like the influence is just gravitational force, but in which direction? So gravity just acts downwards, regardless of the position of the ball. So acceleration is 0. No, this is out. G, now that the acceleration is g and then it's directed downwards, which is the correct direction, and it's g. G directed upwards? No. G directed horizontally? No. G will always be directed downwards. Whether the object was vertically up or vertically down, regardless of the initial direction of projection. Then 1.3, we have a graph that is not to scale, the relationship between the gravitational force and then the mass and its distance. Okay, so this is the distance, this is the force. They are telling us that the magnitude of the force at a distance r is F. Which of the following statements is correct for the magnitude of the force X? Okay, so if the distance is now 6 times bigger. So what do you suggest? Okay. So from the universal law of gravitation, M1, M2 divided by R squared. So we know that if it is R, just capital R, this is going to be the force because F is going with capital R. Now, what if we increase this to 6? So that's going to be G M1, M2 over 6 R but squared. So we know that 6 squared is going to give us 36 R squared. So if I exclude this, okay, I'll be left with just 1 over 36 F. So this whole thing represents F. So 1 over 36 F should be the correct option. Now that's the force. For as long as you increase the distance, the force must also decrease. So D is the best option for this. Then ball M, moving at a speed v to the right, collides with a stationary ball N on the smooth surface. Immediately after collision, ball M comes to rest. And then N moves to the right with a speed v. Which of the following about the collision is correct? 1, total momentum is conserved, and then the masses are unequal. So the first statement is correct. Okay, but then how do we tell about the masses? The fact that the speeds are the same after and before, because this is, one is at rest, the other one is moving with me. After the collision, this one loses the velocity and then just goes to rest, and then this one moves off. So there's no way that the masses are unequal. There has to be something unique. Chances are high that the masses are the same, because it's more like looking at balls of equal masses, and then this one carries the same velocity or carries a velocity v, and then this one just transfers the velocity to that one. And then this one moves off with the velocity. So the masses have to be the same for the velocity to be the same. So total kinetic energy is conserved and the masses are unequal. This is not making sense. I'm not at peace with it. I don't know. I'll see. Let's see. Total momentum and total kinetic energy are conserved, and then the masses of the balls are equal. I'll go with C. Why? Because of the masses being equal. But also D has masses being equal. Okay. Total momentum is conserved and total kinetic energy. So what sort of collision is this? It definitely has to be elastic collision. Why? Because it's going to be M1V plus 0 is equal to M2V plus 0. So momentum will be constant. What about the EK? Same story with the EK. It's going to be M1V squared, and that's going to be M2V squared. Now, for as long as the masses are the same, it means so C is the best option, because this one is telling us momentum conserved, kinetic energy is not. So C is the best. Then 1.5, a small stone is dropped from rest and undergoes free fall. Which of the following below shows the correct gravitational potential, and V, and so on? A stone is dropped from rest, undergoes free fall. So we know that with the energy, if it is at the highest point, it's going to have EP max. And then at the bottom, where it reaches the ground or the surface, it's going to have EK max. So if it's EP max, this is going to be EK minimum. Now I say 0. Then if it's EK maximum, then EP will be minimum. So EK, okay, both graphs, that is that, starting from there, going that side, which is okay. This one and that, which is still fine, makes sense where the graphs are starting from. This and that, okay, this and that is also fine. So all the graphs represent the correct orientation of the EP max and the EK minimum and so on and so forth. Now let us look at some other aspect. Okay. So how will these graphs look like? So chances are high these graphs are not going to be straight lines, because the change that is happening within the energy is not uniform. So I'm going to cross this. I'm going to cross this out because it has a straight line. Let me just focus on just these two. Okay. So if the energy is being lost from the EP, is it going to be this much or this sharp? In other words, is it going to be an inverse proportion? Chances are high it won't. Is the EK going to increase exponentially? Which is correct. So we can see that these two have the same type of graphs. Actually, 1, 2, 3. The EK is just the same. So the issue is for us to highlight the correct E. So I'll go with option C for number 5. Then 1.6, the stationary passenger at a railway station listens to a train approaching at constant speed. So this is Doppler effect. Which of the following is correct for the sound of the approaching train that is heard by the listener? Okay. So for as long as the source is approaching, we expect the listener to get the most, the loudest sound. Okay, and if the sound is the loudest, which means it has to be a higher pitch. And for as long as the pitch is high, Then what's going to happen to the frequency? Let's first look. So this one is out. And then the last option is also out. So that is lower pitch. Now, the observed frequency, since the source is approaching, should also be more, because you tend to hear more of the noise or the sound. So higher pitch, higher frequency, because pitch is how high or how low a sound note is. Then 1.7 particle P and Q, as well as R, have charge of 2Q, separated by a small distance R. Which of the following statements below allowed about electrostatic forces, FPR, which P exerts on R, and FRP, which R exerts on P, is correct. So we're being told particle P has a charge of Q, and then particle R has a charge of 2Q. They're separated by this. They want us to tell about the forces between FPR and FRP. Now, without even doing calculations or what, okay, we can start with that. You know that the force will be K, Q1, Q2 over R squared. That's K. In this case, we have a Q. We're going to have a 2Q over a distance R squared. So which is 2AQ, Q1, Q2 over R squared. Does it make sense? Doesn't matter. Doesn't matter. This is relevant. We know that if two bodies are being separated, the forces that will exist between them will be the same, but just in the opposite direction. So FPR must be the same as FRP. So this is out. I'll take this out as well. I need to have the same values. So we have this option and this option. So which one do we take? I'm going to go for the last option. Why? Because if P is experiencing a force as to Q, let's say the force will be in that direction, and then this one's force will be in that direction. Okay? The forces have to be the same, but opposite from Newton's third law. Okay, then 1.8, so the same thing applies to universal gravitation. So will be the charges. 1.8 is electricity, battery of EMF of that and that. Negligible resistance, there's an internal what resistance, and so on. So which of the following combination about the ammeter reading will be correct when the switch is closed? Remember, ammeter reading is giving us the value of the amount of electricity that is flowing within the entire circuit. Okay, let's look at option A. Ammeter only reads the current in R1. This is wrong. Because remember this, where the ammeter is located, it's going to read the current of the entire circuit, which means this current that is passing through R1 and R2. I don't even need to, wait a minute. Why am I doing it like that? Let me read nice. They're telling us if the switch is open. Okay. If the switch is open, will it make any difference? Ammeter reads only R1. It's still wrong. Because the moment you open or close the switch, I mean there's a connection through R1. It's not a big deal. Only thing is that there's just an alternative path for the electricity that side, or even a short circuit. Okay, so that is wrong because it's just not R1. R2 is part of it because the two tend to be in series, or I can say this whole part is in series with R2. So that is out. We're not going for that. Then ammeter. So this 7 is also wrong. Ammeter reads only the current in R2. That is wrong also because it's both. Ammeter reads the current in both R1 and R2, which is correct statement. Let's look at this side. If we close it, if we close this, ammeter reads the current in R1 and R2. No, it's not going to do correct. Because now, the moment you close the switch, there is no resistance here. There is resistance this side. So the current will just go through straight via that channel. So which means the only current or the only resistor to focus on is R2. I don't know, what's option 4? R1 and R2, and then just R2. So option D is the best. 1.9, the direction of an induced current in a coil of a generator depends on ... The length of the coil, the speed of rotation, direction of the magnetic field, the strength. But this is out. Does that make sense? 1.9. Saying it's out. Why am I saying it's out? Because it just stands out compared to the rest. Okay. How does the length influence direction? How does speed influence to? Doesn't. How does the strength of the field influence? No. So all these ones will just work on the amount of induced current or induced EMF. So C, the direction of the magnetic field. That will tell us more about the direction of the induced current. Okay, then 1.10, the work function of a zinc is greater than that of magnesium. Which of the following statements about threshold frequencies is correct? So remember, threshold frequency is just the minimum frequency needed to eject an electron from a metal surface. So the threshold of zinc is greater. So if zinc is having a greater work function, remember, work function is HF naught. So if the work is greater, which means even the frequency will be greater. So zinc than that of magnesium, that makes sense though. Makes sense. Threshold of zinc is smaller, no, both, no. Threshold of zinc and that are independent, no. So A would be the best. Okay, let's move on to question number 2. Okay, this mechanics now. A person pushes a lawnmower of mass 15 kilograms at a constant speed. Pay attention to this constant. So I know that the mass is 15 kilograms of a flat surface with a force of 90 newtons. So force applied is 90 newtons. And then it's directed along the handle. The handle has been set at 40. Okay, the horizontal, refer to that. And then they want us to draw a free body diagram for the lawnmower. Free body diagram for the lawnmower. So when I look at the lawnmower, I can see that this force applied is in that direction, which can still be translated to that sort of direction. Then we have the weight, we shall have the normal force. And then is there friction? Definitely there has to be friction. Definitely, because it's grass. So with what I'm going to do, since it's 4 mass, so I need a minimum of 4 forces. So I can indicate my N, and then I can indicate my weight. I can indicate my F friction, and then the force applied, since it is just in that direction. So in most cases, we dislike the components of forces, just want the forces themselves. Then 2.1.2, why is it correct to say that the moving lawnmower is in equilibrium? Okay, what would be the explanation? This for 1 mark. So we could say that it's in equilibrium because the lawnmower is moving at a constant speed. And for as long as it's a constant speed, the net force is 0. The left-hand side is equal to the right-hand side. Okay, the force being applied, which is just a component, should be equal to the frictional force. So we can say that it's moving. Okay, it's moving at a constant speed. Moving at a constant speed. Thus the acceleration. Thus the acceleration is 0. Okay. And then they want us to calculate the magnitude of the frictional force acting between the lawnmower as well as the grass. Okay, so since we already know that it's moving at a constant speed, let me just try to break this down. If this is a 40 with a horizontal, which means this is also 40. Okay, if I try to resolve this applied force into components, it's going to be in this sort of direction, down and okay, so it's going to be F, the sine of 40 is going to be F cos of 40. So looking at the number of forces that are acting on the lawnmower horizontally, I'll only have, I can start by saying F net is 0, or F net is equal to MA. Then my F cos of, it's fine, I can say cos of 40 should be equal to my frictional force. So that's a 90 times the cos of 40. Okay, so I put that into my calculator. I end up with 68.94. Okay, 68.94 newtons. Since the direction of motion is just horizontal, then we focus on the horizontal component. Okay, then the next part, they're telling us that the lawnmower comes to a stop. Okay, calculate the magnitude of the constant force that must be applied through the handle in order to accelerate the lawnmower from rest up to 2 in a time of that. So we have our V initial as 0. The velocity with which the lawnmower is moving is 2 meters per second, and then within a time of 3 seconds. Assume that the frictional force between the lawnmower and the grass remains the same as 68.94. What is the question asking for? Magnitude of the constant force that must be applied. Okay, so that does not take away, what do you call this thing? It does not take away the 40 degrees at which a applied force is acting. So you can start by determining the acceleration of the lawnmower itself, okay? We can say that our V final should be equal to V initial plus A multiplied by delta T. Okay, so our final velocity, if it's a 2, the initial is 0, because they told us that it's moving from rest. Plus now the acceleration multiplied by the 3 seconds. So when I divide both sides by 3, my acceleration becomes 2/3, which is a 0.6, I can say 7 meters per second. Okay, so that would be just the first step. Then if I apply, where should I write this? Let me just jot it here. If I bring in the F net is equal to MA, what I need is the constant force, which is F. But we know that the horizontal component has to be F, the cos of 40. So that's what I'm going to use. I'm going to say F applied minus my frictional force should be equal to the mass of the lawnmower. They told us the mass, which is 15 kilograms. Okay. Multiplied by the acceleration that we just got up there. So this is going to be F applied, the cos of 40, minus our 68.94. Okay, should be equal to 15 multiplied by, let me use 2 over 3 straight away, just to avoid the decimals. So this is going to be F cos of 40 is equal to, that's going to be a 10, because by 3, 1 by 3 is 5. So 10, when I add that, I'm going to have 78.94. And then when I divide both sides by the cos of 40, so 78, okay, divided by the cos of 40, I end up with 103.05 newtons. So that should be our force applied. All right, so that is that. That is that with that question. Then 2.2. A planet Y has a radius, okay, of this much, and then a 10 kg mass weighs 20 newtons on the surface of planet Y. Calculate the mass of the planet Y. Okay, so one thing we know about Newton's law of universal rotation is that the force that is experienced between the bodies must be the same. Okay, so regardless of how big or how small it is. So if a 10 kg is experiencing this much of force, which means the 10 kg must also apply this much of force onto the planet Y. So from F is equal to G M1, M2 over R squared. So which means my force is going to be 20. The question wants the mass. So if I called my G to, no, I know my G from the information table, 6.67 times 10 to the negative 11. I'm multiplying it by the 10, multiplying it by the mass of Y, and then they told us the radius is 6, that's just going to have 6 times 10 to the 5. Everything must be squared. Okay, so I can simplify the right-hand side, can exclude that my. So 6.67 times 10 to the negative 11. Okay, I'm multiplying it by 10. And then I'm dividing everything by 6 times 10 to the exponent of 5. That's squared. That's giving me 1.85. So 8 times 10 to the negative 21 my. And then I have to divide both sides by that. So I'm going to say my 20. Let's just have that. And then we're saying 20 divided by my answer. I'm getting 1.079, so which is like 0.8 times 10 to the 22 kilograms. Okay, guys, so that is question number 2. Then question number 3, we're being told that a ball is thrown vertically upwards. okay, with a velocity of v from the edge of the roof that is 40 meters tall. The ball takes 1.53 seconds to reach the maximum. Okay, so might is 1.53 seconds. Ignore that. Can we define free fall? So free fall is just the motion of an object under the influence. Okay, under the influence of gravity, or you can just say gravitational force. Then 3.2, calculate the magnitude of the initial velocity v. So it takes 1.5 to reach the maximum. So we know that at maximum height, okay, I'll say height max, the final velocity must be a 0. So I can use the first equation of motion. V final is equal to V initial plus the A delta T. So my V final, we say is a 0. V initial is what I want, but we know that G is going to be 9.8 multiplied by 1.53. Now, the direction that you use for the G will matter. Let me take downward to be positive, and since we're going up, I'm just going to use negative, okay? So then I have 0 is equal to V initial minus 9.8 times 1.53. That gives me 14.99. Then I'll move it that side. So my V initial is 14.99 meters per second, which is more or less the same as 15. I don't know. I'll just leave it as that. It's fine. Then 3.2.2, calculate the maximum height that is reached. So we can still use the effects that we have, that the delta T is 1.53. The V final is 0, and then we're looking for the displacement. So you can use, we can choose to use the V initial. Either way, we have to use the V initial, because if I look at my displacements, V initial multiplied by time plus a half G delta T squared. Either way, there is V initial. If I use V final squared, it's going to be V initial squared plus 2 multiplied by G delta X or delta Y. So either way. So let me use this second and say that my delta Y is going to be the V initial. My V initial is 14.99 multiplied by the 1.53. Now I'm going to use minus a half times 9.8 multiplied by 1.53 squared. Now you can use a plus, yeah, but then the value of the sign next to the G should be a negative. That's if we're using the same direction as my soap. So 14.99, okay, times 1.53 minus a half times 9.8 times 1.53 squared. I'm getting 11, something. 11.47 meters. So that is the height, or the maximum height, 11.47. All right, so that is 3.2.2. Then 3.3, can we take the edge of the roof as the reference point? We need to determine the position of the ball relative to the edge of the roof after 4 seconds. So from this point of projection, if this is our 0 line, that's what it means to take it as a reference point. So after how long? Or after 4 seconds, what will be the position of the ball. So I can still use the same formula of the delta y, but where there's time, I can just use the 4 seconds. Is that okay with people? Good. So we said we're using the same formula. So delta y is equal to V initial times delta t plus a half g delta t squared. Okay, my delta y. So let me just correct this, guys. It's supposed to be A. Let me even correct this. It's supposed to be A because A is the formula. We don't have G in the formula. So let's write the formula down. You get that mark. And then the substitution, then you replace A with a G. Okay, so V initial, we said is 14,99. Now we're looking at 4 seconds plus a half. That's going to be negative 9,8 times 4 squared. Okay, if I punch that into my calculator, saying times 4 plus 0,5 multiplied by negative 9,8 multiplied by 4 squared. That gives us negative 18,44. Okay. So one thing we need to know is as long as an object moves from the point of projection, reaches maximum and comes back to the point of projection, we call that a displacement to be 0. Then afterwards, this 18,44 is just the distance below the building or below the reference point. So we interpret the negative sign by telling us the position is 18,44 meters downwards, or we can say below the top of the building, below the edge of projection. Edge of projection. All right, then 3.4. We'll end of the answers in 3.2 and 3.3. Change if the height of the building is now 30 meters. Choose a yes or a no. Now, looking at what we've been working with in 3.2 and 3.3, I mean, we've not applied this height in any way. Okay. So the fact that this 40 is not in any of our calculations and it does not have an effect on the maximum height that the ball must reach, I mean, there's not going to be a change. Because remember, we are ignoring air resistance. I mean, if air resistance was there, then we would say that yes, it might have a change. But since air resistance being excluded, our answer is going to be a big no. Okay, it's a no. And what is the reason? It's saying that motion of the ball is only independent. Should I say independent or dependent? Let's use dependent. Dependent on initial velocity. It does not depend on the point of projection or what. Okay. Then someone says, will that give you 3 marks? Yes, to give us 3 marks. Remember, we took a stand to say it's a no. And then our explanation can give us the other 2 marks. All right, then question number 4. This is momentum. We also looked at it. They're telling us that a soccer player kicks the ball of mass 0.45 kilograms to the east. And then the ball travels horizontally at the velocity of this. Okay, I'll just write this there, 9 meters per second, along a straight line without touching the ground, and enters the container lying at rest. I mean, the soccer player should be a star. That's magic. Okay, then the mass of the container is 0.2 kilograms. And we know that its velocity is at 0. Then Okay, maybe this 9C. Okay. The ball is stuck in the container after the collision. And then the ball and container now move together along a straight line towards the east. So the direction is still the same. Okay. Then they want us to state the principle of conservation. Okay. So remember what we said? That in an isolated system, okay, any isolated system, the total linear momentum stays constant or remains constant or stays the same or is conserved. Can use those things. And saying an isolated system, total linear momentum remains conserved. Okay. And then 4.2, they want us to calculate the magnitude of velocity of the ball and the container immediately after collision for 4 marks. So let's just use the principle of conservation. So I'm going to say that if I get the mass of the ball, velocity initial of the ball, plus the mass of the container, velocity initial of the container, must give me the mass of the ball plus the mass of the container multiplied by the combined velocity. Okay, so this is what we want. So the ball is 0.45. Okay, they told us it's moving at 9 east. Plus the mass of the container, it was 0.2, but initially it was at rest. This gives us 0.45 plus 0.2 times V. I'll say V final, it's fine. So this dies out to a 0. Then I'll be left with 0.45 times 9. That gives me 4.05 is equal to 0.65 VF. Then divide both sides by 0.65 over 0.65. That cancels that. So my VF is something like 6.23 meters per second. Okay, so that is 4.2. And then 4.3, determined by means of statistical calculation whether the collision between the ball and the container is elastic or inelastic. So remember what we said. As long as a question of this nature comes, the first thing you need to go for is the kinetic energy. Okay, so go calculate the EK before, and then we also look at the EK after. So for the EK before, I'm going to say it's a half mass of the ball, velocity of the ball squared, plus a half mass of the container, velocity initial of the container squared. This is initial. When I do my substitution, it's going to be a half times 0.45 times 9 squared. This is going to die out because the initial velocity is a 0. So that's going to be 0.5 times 0.45 multiplied by 9 squared. That's giving me 18.225. So this is energy to be in joules. Then let's get the EK after, which will still be the same as a half. This is now going to be the combined mass since the two are moving together. Mass of the ball, mass of the container multiplied by the velocity that we got. So it's 6.23. We square that. Okay, so that's going to be a half. Mass of the ball was 0.45, but we saw the combined mass. Why am I stressing myself? Which is, we said 0.65 multiplied by 6.2 squared. What we get? Okay, multiplied by 0.65 multiplied by 6.2 squared. I'm getting 12.49. Remember, this was 18.225. This is 12.49. So just by looking at this, I can already see that the kinetic energies are not the same. And the fact that the kinetic energies before and after are not the same, therefore the collision is inelastic. The reason EK before is not the same as EK after. Okay. Question number 5. Here we saw also energy. So I believe this will be the last question. Then we go back to the guideline. Okay, a 70 kg box is initially at rest, okay, at the bottom of a rough surface. This word is important, it's even in capital letters. At an angle of 30, okay, to the horizontal, the box is pulled up by means of a lightning eccentric string held parallel to the, okay, force applied is 700, good. What is the name given to the force in a rope? So all ropes, all strings, they usually possess one force, and that is the tension force. So the force there is tension. Please don't tell us force applied. It's the tension force. Okay. Then 5.2, give a reason why the mechanical energy of the system will not be conserved as the box is pulled up the plane. So the reason for this, okay, why energy is not going to be conserved, because the surface is rough. I mean, as you're trying to pull it up, friction is trying to pull the box downwards. So in that way, you'll have to cover up for the losses and all of that. So we can say that the presence of friction, the presence of the frictional force, we can also say the tension in the system. Both tension and frictional force will have an effect on that. Okay, then the box is pulled over a distance of 4 meters. So from here up to there is 4 meters. And then the kinetic frictional force between that is 178,22. They want us to draw a free body diagram as the box, or for the box as it moves up the incline. Okay, so with this, before I even draw the free body, just look at the forces that are going to be acting on the box, the way it is. So we know that this is going to be the force applied. Whenever we have an incline, it's automatically that the FG parallel will always act downwards. Okay, remember we said we don't want components, but I might be forced to put it. So frictional force is also going to act downwards. And then we're going to have the weight and then the normal force, the N up. How many marks is it? It's 4 marks. So if we can have just 4 forces, that will be good. Okay, so we're saying force applied, and this force applied is in the form of the tension. Okay, and then we can also have the frictional force, which is F. And then we say the normal force, and then we can have our weight, which is also okay. Alternatively, you could have the normal force, the tension, even this component, FG parallel, because it's acting downwards anyway. Okay, because our focus is just going to be the motion along the incline. So you could also indicate it the FG parallel. Okay, so that is the free body diagram. These two have to be in a straight line. I don't know why mine is Q. I know it's a weekend, but good. Okay. Then 5.4, they want us to calculate the work done on the box by the frictional force over the 4 meter. So from our formula page, we know that the formula for work done do we have it here? It should be here. So this formula here is what I'm going to use. Okay. So we're going to have W work done by the frictional force, I'll just call it WF, is equal to F multiplied by the delta X and then the cos of theta. So my frictional force is 178.22 multiplied by the displacement, which is 4 meters. And then I'm going to use the cos of 180. Why are we using 180? We know that the object is moving up the incline. Okay. So up the incline will be our reference point, which is a 0. But then frictional force is acting on the opposite, which means it's acting within an angle of 180 in the opposite direction. Okay, that's why I'm using cos 180. So I punch that into my calculator. That's going to be 178.22 times 4 the cos of, we said 180. That's correct. So that's going to give us negative 712. Okay, 88. Remember, this is work done. Work done is measured in joules. So the explanation for the negative sign is just the direction. It's acting in the opposite direction. All right, then 5.5, use the energy principle to calculate the speed of the box after it has moved 4 meters up. I need space. Okay, let's just explain this nicely. So one thing we know about energy principles. Remember, we said we have WNC is equal to the change in EK plus the change in EP. But we also say that the net work done should be equal to the change in the kinetic energy. Okay? So I think I can use this one for me. The net work done should be equal to the change in kinetic. So in that way, I'll have velocity involved straight away. So let me just scratch this out because I need space like badly. All right, so for the network, since the direction is up and there's just one force that is working up there, so I'll look at the, let me not use that. We're saying net is going to be the work done by the tension, okay, plus the work done by the frictional force, and then the work done by the FG parallel, because from our free body we saw that FG parallel and F frictional force are acting in the same direction. Okay, let me just get this first. So work done by the tension is going to be 700 multiplied by 4 multiplied by the cos of 0, since it is acting in that direction. And then the work done by the frictional force, we already got it as 712.88. Then plus the work done by the FG parallel, we know that the force FG parallel is given as the mg sine of theta. Okay, so this theta is this angle of inclination. The cos theta here has to do with just the direction of motion. Okay, so I'm gonna use this formula and say the mass is 70 times 9.8 multiplied by the sine of 30. So that's just the force. I'm multiplying it by 4 and then the cos of 0. So if I try to substitute this or punch that into my calculator, first, so 700 times 4 cos of 0, I'm getting 2.8. Okay, negative 12.88 plus 70 times 9.8 sine of 30. And then I'm multiplying by 4 cos of 0. So this is giving me 3459. 3459, 12. So this is just the network. Okay, so we say network must be equal to the change in kinetic energy. So the change is going to be a half m. It's going to be v final squared minus v initial squared. I think that's how I can best put it. Okay, so I'm going to equate all this to 3459, 12. We know that the mass is 70, so a half of 70 is 35. Then I'll divide both sides by 35 and then replace all the other information. So what do we want? We want the initial velocity. Calculate. Calculate the speed after it has moved up. So which means we need the final velocity. Initially, this thing was at rest. If I am not in forward, is at rest. Perfect. So which means the initial was a 0. So which means our VF squared should be equal to this divided by 35 and then under the square root. Okay, so let me divide this by 35 because a half of 70, I'm getting 98,832. And then I need to find the square root on either sides. All right, square root is giving me 9,94 meters per second. Okay, 9,94 meters per second. So guys, that's how we would have obtained those 5 marks. I don't know if there are other options of how to get that, but this is how I'm getting mine. This is how I'm getting mine. Someone is saying, let's go back to the calculations and just confirm. Yeah, there's a problem. There is a problem. There's a problem. Okay, let me just, because I've seen my mistake. So this is going to be wrong. Same applies to that. So the wrong thing is this part. Okay, remember we said it's 70 times 9,8 sine of 30. I'm multiplying it by 4 and then the cos of 180. Why are we putting the cos of 180? Because it's also acting in the opposite direction. Thank you for that. So this is also not in. This is also out. So I'll have to redo it again. So 700 times 4, cos of 0, we said negative 712.88. Okay, plus 70 times 9,8 sine of 30 times 4, and the cos of 180. I'm getting 715. Okay. Comma 12. 715, comma 12. I'm going to divide it by, we said, 35. This is going to give us 20. So VF squared is 20,432. Because remember, this is a 70, then simplify. So the square root of that, square root, I'm getting 4,52. 4,52. That is meters per second. Thank you very much. Okay, then we move on. So we have to erase this also. You say it's 4,52. Then when the box is 4 meters up the incline, the rope breaks, causing the box to slide back down the bottom of the inclined plane. What will the total work done by the frictional force when the box moves up and then down the incline to the bottom? Okay. So looking at the work done by the frictional force, remember we got it as negative this much. This was just to move up a box, which means even when the block is sliding down, the same amount of energy will be done because it is still the same surface, the same coefficient and everything. So I'm just going to say 712,88, and then I'm just going to multiply it by 2. So 712,88 multiplied by 2, which gives me 1425,76 joules. But that will be negative. All right, so that is question number 5, and that is the work, energy, and power. All right, then we go back to our guideline where we have the next topic being Doppler effect. So Doppler is a grade 12 topic, which is not carrying that much of marks. So all we need to know is at least state Doppler effect in words. Okay, and we're being told that it is the change in the frequency of the sound detected by the listener because of the sound source and the listener having different velocities relative to the medium of sound propagation. So find sweeter words, or you can just use exactly this. Okay, but for as long as we have words like relative velocities, okay, then the difference, you said change or difference in the frequency by the listener because of the sound source and listener having both. So we just need to know also how to explain using illustrations the change in pitch observed by the source as it moves towards the listener or away from the listener. Okay, this could be explained through, let's say, some drawings. Okay, we've seen cases where we have such circles that are moving towards one point and then so on and so forth. And then we need to know when is it moving away, when is it moving towards, and stuff like that. Then we also need to remember this formula, the Doppler formula. Okay, so remember we have 2 signs on top and 2 signs down. When do we use which format? Okay, an example, if we're looking at the frequency of the listener, and let's say the object or the source is moving towards, so which means it's going to be V plus VL over V minus Vs times the frequency of the source. So why are we using plus and minus? Because we know that when the source is moving towards the listener, we expect the frequency heard to be bigger. And for us to have this right-hand side to be bigger, there has to be a plus on top, and then the bottom has to be smaller. Then if it's moving away, it's just the opposite. Just switch the signs and then they're around with that. Then we need to look at the applications of Doppler effect and which machines, like in the Doppler flow meter. What is the use of the Doppler flow meter? We also have the radar machines that are used to detect the speed of cars and so on and so forth. Yeah. Then still under this, we need to also do explanations with the red shifts and the blue shifts and all of that. Okay. Then the next topic, I'll just combine the 2. Okay, from here, we have electrostatics. So this was mainly done in grade 10 and 11. So there's nothing new to add on to that. So whatever knowledge we gained in grade 10 and 11 is basically the same knowledge that must be carried on to grade 12. Okay, so we need to know how to state Coulomb's law. That the magnitude of electrostatic force exerted by one point charge to another is directly proportional to the product to the magnitudes of the charges and inversely proportional to the square. So this and the Newton's law of universal gravitation are just the same things. But as long as you get to know one, just change that side from masses and then bring charges here. The rest is history. Then 2, you need to solve problems using this formula. And then we said we're only going to use 3 charges. We can't go beyond that. Then we also solve problems using this, as long as we're looking at 2D. So 2D is basically, okay, 1D is where the charges are just in one straight line. 2D, 3 forces, but maybe they are forming some sort of a rectangle or a vector kind of drawing. All right, then electric field, you need to describe, know how your definitions work. Regional space in which an electric charge experiences a force, or regional space in which a charged object experiences an electric force. Direction of this is the direction that a positive test charge would move if it was placed at a point. How do we draw electric field lines? Let's say with a single point charge, we know that with positives, the field lines or the arrows must be seen moving away. Okay, and then with the negatives, the arrows should be seen entering. Okay, and then if you have, let's say, 2-point charges, just need to know how they work. The opposite charges will always attract each other, and then the negative charges will repel. Then for as long as the charges have the same magnitude, just pay attention to the number of field lines, and also know that these field lines do not cross each other. Okay. Then they said we're going to restrict this to just charges with that are identical in magnitude. Okay, beautiful. Okay, define what electric field at a point is. Okay, it's a point electrostatic force experienced by unit positive charge. So just know how to define that and also the formula. How to solve problems using that and calculate the electric field at a point using this formula. So this is derived from that. Yes, we're saying the force, which we said was K, we're going to use Q and then Q over R squared. And then you're saying you're dividing it by 1 over. So this cancels that. Then you're left with. So Q is just the normal charge, and then the small q is just the point charge. Okay. So that is that. Let's look at the sample questions and we see. Question number 6 in this case. They're telling us that a patrol car is moving at a constant speed towards the observer. Okay, so the scenario changes. It's moving towards. The driver switches on the siren when it is 300 meters away from the observer. Okay. The observer records the detected sound waves of the siren as patrol car approaches, passes, and moves away. Information is given on the graph. Wow. This is interesting. Okay, so approaching, probably around and then moves away. Does that make sense? Approaches, passes, moves away. All right, then they're asking us to calculate the velocity of the car. Okay, so if, I don't know, let me just, I love drawing so much. So if this is the source, this is the observer or the listener, they're telling us that the distance there is 300 meters. But we already have the frequency. Okay, the frequency is 932. So at this point, the listener is getting a 932 hertz of frequency. How do we get the velocity of the car? Which formula can we use? Do we have the time? There's no time. What else do we have? Okay, yeah, we have this 10. Yeah, 10 seconds. So this 93 watts is going to last for 10 seconds, which means that this car, the vehicle, is going to move for 10 seconds before it gets to the observer. All right. So if I use speed distance over time, which is 300 over, which is 30 meters per second. I don't know. That's what I'm getting. I'll take that. So state Doppler effect, remember what we said? That the change in the frequency of a sound detected by the listener, because the sound source and the listener have different velocities, that is relative to the medium or the sound or medium propagation of sound. Okay, then 6.1.3, they're telling us the detected frequency at this. What is the question saying, guys? I'm saying the detected frequency suddenly changes at this. And what is the reason for that? Okay, so the changes, I mean, if the car just comes and is making a lot of noise and immediately it passes you, definitely there's going to be a change. Okay, so we could say that the car just passes the listener or observer. Okay, that is one reason. Or you can just tell us the car starts to move away at that instant, and can also tell us that maybe the car and the observer are just in the same place, because the moment you're just at the same place, then there's going to be that change. And then 6 point, next, they want us to take the speed of air to be 340 and then calculate the frequency of the sound emitted by the siren. So what we saw was that the frequency of the listener was 932. Okay. The velocity of the source was 30 meters per second. The velocity of the listener was 0. The velocity of sound is 340. Why am I saying Vs? It's supposed to be just a V. Okay. So I think, what do they want? They want the frequency of the source. All right, so remember what we said? Frequency of the listener should be V plus minus V what? VL over V plus minus Vs times F of S. That's the formula. Let's just go back there and be sure. Let's listen on top. Perfect. Okay, then let me do the substitution. This is going to be 932 is equal to my 340 minus velocity of the listener is 0. Am I using a minus? That's going to be a plus since it's approaching. Okay. Then this is going to be 340 minus the 30 times the Fs. 932 is equal to 340 over 310 times Fs. All right, so 340 divided by 310 is giving me a fraction when I'm, what fraction is it? 34 over 31. Okay. Fs is equal to 932. And then divide both sides by this thing. So 932 divided by my answer, I'm getting 809.76 hertz. Okay, so that is the frequency of the sound, 849.76 hertz. Okay, state two applications of Doppler effect. Remember, we said it can be used in the Doppler flow meter. Okay, that meter that is used to measure the heartbeats of the fetuses and all of that. Two applications, okay, in the Doppler flow meter. And then we also said they can be used in the speed radars to detect those speed cameras and things, okay. And then we could also look at the sonar, okay. And then also to detect the moving stars and all of that. So all those are applications of Doppler effect. Question number 7, electrostatics. 2-point charges Q1 and Q2 are placed 30 centimeters apart along the straight line. Q1 is this, the point P is 10 centimeters, okay. As shown, the net electrostatic force is 0. So F net is 0. All right, then define the term electric field at a point. Remember what we said? This is the electrostatic force, okay, experienced per unit positive charge placed at that point. Okay, you can just go back there and then you just read our definition. Electric field. All right, then state giving reasons whether the point charge Q2 is positive or negative. State giving reasons. Now, the fact that we're having two charges, one of which is negative, and then we have a net force of 0, then chances are high that this Q2 is going to be a positive. Why is it a positive? Because it needs to counter this negative force or the negative direction so that there is some sort of attraction between the forces themselves. Okay. So we're going to say that the electric force due in Q1 will be negative. No, not really negative, but the direction will be different, because if this point charge is positive, so which means the force applied here is going to be force experienced, that this is going to be to the left. And then if this is a positive and this is a positive, then the force is going to be to the right. There's repulsion and what. So that's why I'm going for positive. Okay. So explanation, we're going to say that since the E net is definite, electrostatic field is E, not F. Okay, so we're saying the E net is 0, E1 and E2. So E1 and E2 are in opposite directions. They have to be in opposite directions. All right, so that is that. Then I want us to calculate the value of Q2. So we have to use the electric field. So remember we said E is KQ over R squared. Okay. So I'll start with the first one, which is Q1. 9 times 10 to the 9 multiplied by 3 times 10 to the negative 9 divided by 10 changed to meters. That's going to be 0.1. I'll square this. Now, since we know that our E net is a 0, which means the E1 must be the same as the E2. Okay, let me simplify that. I'm having 9 times 10 to the 9. I'm multiplying this by 3 times 10 to the negative 9. This is over 0.1 squared. I'm getting 2.7. Okay, let me look at E2. E2 is saying it's going to be K, which is 9 times 10 to the 9, multiplied by Q2 over the distance. Now it's going to be 40 centimeters, which is now 0.4 squared. If I simplify that, I'm going to remove that, put a 4, going to remove all of this. It's going to give me 5,625 times 10 to the 10 Q2. But remember, E net is 0, so which means E1 and E2 have to be the same. So this is the same as 2.7. Divide both sides by 5,625 times 10 to the 10. So when I do that, I'm going to have 2.7 divided by my answer. Getting a weird answer. It's very weird. It's 4.8 times 10. 1, 2, 3, 4, 5, 6, 7, 8. This is it's negative 8 coulombs. Okay, or you can just give it to us as 480 microcoulombs. 480 times 10 to the negative, or 480 microcoulombs. Yes, perfect. All right, then 7.4 state coulombs law in words. Remember what we said? That's more like the definition of electrostatic force. We're saying the electrostatic force between 2-point charges is directly proportional to the product or to the product of the magnitude of the charges, but it's inversely proportional to the distance of separation, to the square of the distance of separation. Then calculate the magnitude of the electrostatic force exerted by Q1 on Q2. So we already have the Q1. Now we calculated our Q2, which is now 4.8 times 10 to the negative 8. So let's just get the force. Remember, the distance is 30 centimeters. So force, we said it's K, Q1, Q2 over R squared. So 9 times 10 to the 9. This is going to be 3 times 10 to the negative 9. And then times 4.8 times 10 to the negative 8 over 30, which is 0.3 squared. And then I just get my force, punch this into the calculator first. 9 times 10 to the 9 times 3 times 10 to the negative 9 times 4.8 times 10 to the negative 8 again over 0.3 squared. That gives me something weird again. I hate this, mustn't it? So it's 1.44 times 10, 1, 2, 3, 4, 5 here. So it's negative 5. Remember, it's a force, so it's newtons. All right, then 7.6, we've been given point charges and they drew for us the fluid patterns. So 2 charges are now brought into contact with each other and then separated. So whenever this happens, after the separation, the 2 charges will have the same magnitude. And the same sign, which means we expect some bit of repulsion afterwards. All right, so with this one, they are telling us that a learner draws the electric field pattern for Q3 and Q4 after contact. Is the diagram correct? The 2 charges are now brought into contact. So, is it still connected to this? Yes. This is a negative 3. This is a positive 4.8. Okay, so if you combine this, let me just be sure, 4.8 times 10 to the negative 8, I'm saying plus negative 3 times 10 to the negative 9. Okay, I get a positive answer. I divide it by 2, so which means it's correct since the field lines are moving out. So the answer is a yes. Okay, because both charges are positive and equal in magnitude. All right. Then question number 8, which is electricity. So, and electricity, we just need to know about Ohm's law. Okay, how do we state Ohm's law in words? So the potential difference across a conductor is directly proportional to the current in a conductor at a constant temperature. So this is important. Then the directly proportional part is also important. So those keywords, at least they shouldn't miss in your definition. And then the relationship between current, potential difference, and resistance at a constant temperature for a simple circuit. You need to know that difference between ohmic conductors, those that obey Ohm's law, and then the non-ohmic that disobey Ohm's law. Then we solve the problems using this Ohm's formula for series and parallel circuits. We need to know the difference between the two and what happens in the series, because many times circuit diagrams are given and then we fail to notice what's happening. So one thing we need to remember is that for parallel circuits, the velocity, not velocity, it's the voltage, which voltage is also known as the PD, is always constant across. For series, it's the current that is constant. Okay, then power energy, define what power is, rate at which work is done. This is the formula. And then the different formats of power, okay, right from there. Then solve circuit problems involving concepts of power, electrical energy, deduce that 1 kilowatt hour refers to that, calculate the cost of electricity, okay. And then the great over aspects of internal resistance, series and parallel, and then EMF also needs to be understood quite well, okay. How do you define EMF? And so on and so forth. Okay, so let's just focus on this electricity, then we shall come back for electrodynamics. Okay, so 3 resistors, and light bulbs are also resistors. A, B, and C, each are rated 6 watts and 12 volts. Define the term power. Power. So we say the simple one, rate at which work is done. Okay, the rate at which work is done, or the rate at which energy is transferred. You can say that. Or rate at which energy is converted. Any other definition is also acceptable. Then 8.1.2, calculate the resistance of each bulb when used as rated. So we have the power, we have the voltage. What do they want? The resistance R. So we need to look for a formula of power that has resistance involved. So if I have P is equal to IV, but I know that V is IR, so which means I'm going to use P is equal to, no, that's not going to make sense. Let me make I the subject, which means it's V over R. So V squared over R. So which means that my resistance is going to be V squared over the power. My V is 12 over 6. So 12 squared over 6. What do we get? We get 24. I'm getting 24 ohms. Use any other aspect of power. Remember, we said we have different formats of power. But as long as it has resistance in it, we don't care. We shall give you the marks. Our job is just to give you marks, as long as you write the correct thing. Next, the light bulbs are connected in a circuit with a battery that is having EMF of 12 volts and an internal resistance of 2 ohms. I think this was meant to be that small e, and that is the ohm symbol. All right. This is what they do for us, and this is how they are connected. Assume that the resistance of each light bulb is the same as calculated before. So this is a 24 ohm. This is also a 24 ohm. And then even this one is a 24 ohm. Okay. What is the first question asking for? They want the total current within the circuit, 5 months. Yo. Okay, so I can use the EMF formula and say it's I into R plus R. It's told us EMF of this. So we have the EMF of 12, the internal resistance, we have it. Do we have the current? We can get the current since we already have the power and the voltage. Okay, let me start with that. So power over, are we still on the same thing? No, I'm not gonna do that. I'm not gonna, that is going to be risky for me. Let me start by getting, what is the question asking for? They want the current. So if I use that, I'll be committing suicide. Okay, this I don't know. It's a different question. So I need to get the capital R first. Okay, so resistance external. So I see that B and C are in parallel. And then A is in series with this parallel combination. So let me just get the R for the parallel. That's 1 over R1 plus 1 over R what, and I prefer using product over the sum. So that is going to be 24 times 24 over 24 plus 24. Okay, so 24 by 24 divided by 24 plus 24. That gives me 12 ohm. So the combined resistance for these two is 12 ohm. And then since now this 12 is in series with this, which means that my R effective is going to be 12 plus 24, which gives me a 36 ohm. Then come here and substitute, and my current is going to be EMF over R plus capital R. EMF we said is 12. The small r is 2. The capital R is 36. Let's punch this into the calculator and see. 12 over 38. I'm getting 1 over 3. Is that even reasonable? Is that reasonable? 12 over. That's fine. Let's keep it that way. There's nothing to do. So 12 over 38. No, man. That's my calculator. Because when I punch it back, I'm getting 0.315. So it's 2. Okay, we keep it that way. Then, so we have our current here at 0.32 amps. Then calculate the potential difference across C. Now, since we know that this and this one, the parallel one, are in series, which means there's going to be a voltage that is different from this voltage. But the voltage of B is going to be the same as the voltage of C. So I'll start by getting the voltage across. How many mass is it? It's 3 mass. Let me get the voltage across the A. Okay, so we know that the voltage, I'll say V is equal to IR. Let me just get the external voltage. That's going to be the current, which is 0.32 multiplied by the resistance here. Total resistance was what? 36. No? Is it going to be 36? Mm-hmm. It's not going to be 36. How am I going to do that? Because they want the potential difference, which is the V. Okay, let me do this. Let me do this. So without, I'll just include the small r so that I just focus on this. So if my I is a 0.31, no, say 32, into, that's a 24, plus a 2 should give us the V external. Just want the external voltage. So 0.32 multiplied by 26, I'm getting 8.32 volts. Okay, that is 8.32 volts instead of the 12. Okay, then if I get my overall, which was a 12, remember now this is just the EMF across this one. 12 minus 8.32. That's going to give me 3.68. So 3.68 is across the parallel. Okay, and remember what we said, voltage across the parallel is always constant, or it's always the same. So we're going to say that the voltage across is 3.68. Okay, I'll keep that. I'll go with that. Then 8.1.5, can we explain why C in the circuit will not burn at its maximum brightness? Now, the fact that we have an alternative path, okay, or B, okay, that is one. But we can also look at the power ratings. The power rating is 12 volts. This is how much it can handle. But then what is going through there is just a 3, something. So I believe it is too low. It is too low. So how do we put that into consideration or into explanation? We can say that for any resistor, the power is always directly proportional to I squared. Remember I said it was I squared over R, or V squared over R, and inversely proportional. Inversely proportional to the resistance. So which means that however much the power increases, the resistance just tends to decrease. (8.2) resistors A, B, C, and D are connected to a battery that is having EMF and energy given to a resistance as shown. Give a reason why current in A is greater than the current in C. So by virtue of looking at this, it's like A is connected to the line that is going to feed these others. And the fact that C is in parallel with this, there's a division. Okay, there's a current, maybe A, there's a current B. So the current of A should be equal to the current of C plus BD. Okay, so basically, that is the literal explanation. Or you can put it in words and tell us that the total current through A is equal to the current through C, B, and D. Total current through A is the total of that, which means it's greater. It's equal to the sum of that. Or you can tell us that the current through C is just a branch. It's just a portion of that. Then 8.2.2, resistor C is now removed. Beautiful. how will the current in B compared to the current in A? So the answer is going to be the same. Or you can tell us it will be equal to each other. Why? Because for as long as this is out, A, B, and B are going to be in series. And we said in series, the current will be basically the same. Okay, so you can say resistors will be in series. All right, then we move on. We move on. Question number 9, that is electromagnetism. Let's go back here. Said electrodynamics. We need to look at electrical machines, that's the generators and the motors. We need to be able to state the energy conversion in the generators. What does a generator do? What does it convert? So it converts mechanical to electrical. What do motors do? Motors convert electrical to mechanical. Okay, use the principle of electromagnetic induction to explain how generators work. Okay, using those Fleming's left, right hand rule and so on. Explain the functions of the AC and the DC generator. Examples of uses of the AC and DC generators. And then energy conversion in motors. The motor effect, to explain how the motor works. Functions of the components like the slip rings and all those things, the brushes. Examples where motors are used, or uses of motor. And then under this, we also tackle the alternating current, the AC, advantages of AC over DC, sketching the graphs, okay, define the RMS of this. So here is the definition. The difference, define the RMS potential, no, it's not the definition. RMS potential difference is the AC potential difference, which displays the same amount of energy as the DC. Yeah, it's the same. So RMS current is the alternating current, which displays the same amount of that. So we just need to remember that. Then the formula of IRMS and Imax, all this will be given on the formula page. Just know how it works. Okay, back to our practice questions. They're telling us the diagram below shows the voltage output of a generator. Then we have 312, negative 312. Have the time intervals, and then the graph is given to us. So we know that for as long as it is a sine graph, this is a generator, with the motor to be more like amps. Okay, so does this generator have split rings or slip rings? What's the reason? Okay, we're saying the slip rings. It's the slip rings. The 9.2, which one of the diagrams below, A or B, shows the position of the generator's coil at a time 0,1. So you're seeing that at 0,1, the potential difference is 0. So when do we have a 0? Is it when the coil is parallel to the direction, or it is perpendicular to the direction? So we get a 0 when the coil is perpendicular. Okay, when the coil is perpendicular, that's when we have the 0 voltage or 0 EMF. Okay, then they want us to calculate the root mean square voltage of this generator. So from these formulas, we said root mean voltage. So we said Vmax over square root of 2. So Vrms is going to be Vmax over root of 2. So it was 312 over square root of 2. Let's put that into our machines. I'm getting 220.62. 220.62 volts. Okay. Then a device that is having a 40 ohm resistor is connected to this generator. Calculate the average power that is dissipated. So power average, will be equal to V RMS over R. So that is going to be 220.62 divided by the resistance, which is 40. Okay. But just a moment, why am I have to use VR squared, V squared over R. So it's V squared because I'm looking at the power. So I need to square that as well. Okay, so 220.62 squared. I'm dividing it by 40. That gives me 1216,829, which is 83 watts. Okay, and then 9.4.2, they want the maximum current that is delivered by the generator. Maximum current that is delivered by the generator. So number one, we need to start by getting the current itself, okay? That I max. Is it going to be the I max? Definitely. It's going to be, remember, it's V is equal to IR. So I max is V max divided by the resistance. We don't have resistance max. Okay, so our V max, remember, was 312 divided by the 40. 312 over 40, you know the same thing. No, it's 7.8. This is amps. And then for us to get I RMS, it's going to be I max over √2. The question wanted the I max, maximum current. So why am I getting √2 again? No, there's no need for that. That's just fine. Just the formats that look so direct and there's a lot. All right. That is question number 9. And then lastly, question number 10 deals with the photoelectric effect. Okay, so we go back here and we say optical phenomena and properties of materials. Photoelectric effect describe what it is as a process where electrons are ejected or removed from the metal surface when a light of a suitable frequency is shown. When you shine, when the light is incident, then that will be able to remove an electron. What is the significance of photoelectric effect? Define threshold. Remember, it's the minimum. Okay. Then define the work function, which is the minimum work to be done in removing an electron. Then calculations using this. And then we need to know that E is equal to HF, where H is Planck's constant. Then this is the formula for the work function. And then the EK max is given as that. Explain the effect of intensity. So this simply means that if you increase the intensity of the light, what will happen to the number of electrons that will be ejected? Okay, when you change the frequency, what will happen? Then state the photoelectric effect as demonstrates the particle nature of light. Then you also have to discuss emissions and then absorptions, the different spectra and so on and so forth. So this we need to know, at least before we go for the paper. Okay, let's answer this last question. They're telling us a potassium metal plate is irradiated with light of this much wavelength. Okay. In an arrangement as shown below, the threshold frequency of this is this much, and then define threshold frequency. So we say this is the minimum frequency of light needed to eject electrons from a metal surface. So the words minimum frequency and then eject electrons from a metal surface, those are keywords. Then 10.2, calculate the energy of a photon incident on the metal plate. So since we want the energy, remember E is equal to HF. Okay. But do we have the frequency? No. Remember, we're not talking about the light as yet, because this is a potassium metal plate. So a potassium metal plate is irradiated with light of this much of wavelength. This is just the threshold. It's not the frequency that we're just going to. So I think we can use the wavelength formula. So we're going to modify this. We know that F is equal to C over lambda. So where there is F, I'll just put a C over lambda. And then I have this. What does the question want? The energy. So my H Planck's constant is 6,63 times 10 to the, is it 34? Negative, positive. Should be negative. I hope so. Then the speed of light, 3 times 10 to the 8 over the wavelength, which is 5 times 10 to the negative 7. Okay. When I substitute all of this, punch it into the calculator, 6,63 times 10 to the negative 34 times 3 times 10 to the 8, because that is the speed of light. I'm dividing it by 5 times 10 to the negative 7. This gives me 3,98 times 10 to the negative 19. Since it's energy, to be measured in joules. All right, 10.3, use a suitable calculation to prove that the ammeter will show some bit of reading. So what do we do? So for us to have some bit of reading, which means there should be kinetic energy. Okay, so what I'm going to do is I need to get the energy, which will be the work function plus the EK max. Do we have the work function? We can get it since we have the threshold. Okay, so this is going to be H times F. Work function, we said, okay, I'll just keep it. This is a half mv squared. That is the maximum velocity. So then I don't have frequency, so it's H C over lambda again is equal to my work function plus EK max. And then I'll do my substitution. We know that this work function is the same as H multiplied by F naught. So Planck's constant and this whole thing, isn't this what we just looked for? The energy of a photon instant. Yes, that's what we got. So you're going to have 3,98 times 10 to the negative 19 is equal to 6,63 times 10 to the negative 34 multiplied by the threshold frequency, which is 5,55. Okay, times 10 to the 14. That is correct. And then plus our EK max. Then I need to just do the subtraction. Okay, so my subtraction is 6,63 times 10 to the negative 34 times 5,5, 5 times 10 to the 14. Okay, so I'm getting 2,98 times 10 to the negative 20. So this is the EK max. Now, so since our EK max is greater than 0, since EK max is greater than 0, then therefore there is going to be a move. There's going to be some movement on the ammeter reading. There's going to be an ammeter reading. So just that. And then we can show that the electrons are going to have some energy. Now remember, this energy is what the electrons are going to possess. Then 10.4, the intensity of the light is now increased. Explain how this will cause the increase, why this causes an increase. Okay, so increasing the intensity increases the number of photons. And say increase in the intensity will increase the number of photons Remember, photons are just energy packets. Okay. Increase in intensity would increase the number of photons. We can say ejected per second. I think that's our definition, that's our explanation. And guys, so I'll stop there because the rest are just formula pages, information pages that you need to at least know and use and follow. Okay. So guys, I'll stop there and just wish you guys the best in paper 1. So let's meet when we're discussing the possible solutions. Thank you very much and all the best in your paper.